Hello everyone, welcome to this rock test webinar. We're very happy to see so many participants for this webinar on bridges and infrastructure for structural health monitoring. We're confident that your presence will contribute to the interest of this discussion today. Please note that there will be a question period of approximately 15 minutes at the end of the 30-minute presentation. So we're looking at about a 45-minute presentation in total. During the presentation, you can write your questions in the question box on the right-hand side of your screen. We'll answer them directly in the chat, or we will answer them during the question session after the presentation, or we'll answer them by email afterwards. Given this presentation today is my colleague, Roberto Walder. Roberto is from the company SMARTEC. SMARTEC is based in Switzerland and supports rock tests for fiber optic solutions for geotechnical and structural monitoring. SMARTEC is part of the rock test group, and rock test is within the Nova Metrics group that you can see here on this slide. Rock test is based in Saint-Lambert, Quebec in Canada and specializes in instruments for the following applications such as building, bridges, geotechnical, in situ, mining, pipeline, tunnels, etc. So I'm going to give the floor to my colleague Roberto Walder, who has been working for SMARTEC for the last 22 years and is our expert for fiber optic solutions. Thank you for your attention and enjoy the webinar.
Thank you, Olivier. Thank you for your introduction. Okay, so let's start with a very brief introduction on the structural health monitoring, instrumentation, and sensors. Okay, so here we can see the types of sensors by gauge length. So sensors are classified in discrete sensors with constant gauge length and distributed sensors with a variable gauge length, which are typically based on distributed fiber optic sensing. So discrete sensors are divided between short gauge with a typical length from 10 to 100 millimeters and long gauge deformation sensors with a length from 25 centimeters to 10 meters. Distributed sensors can be based on Bridge scattering technology for strain and temperature analysis along the fiber, and Raman scattering technology for only temperature, and finally railing scattering for acoustic analysis along the optical fiber. So long gauge deformation sensors are all fiber optics are based on the interferometric principle or Bragg rating, while short gauge sensors are typically electrical strain gauges, vibrating wires, and also fiber optic Bragg ratings and Fabry-Perot cavity sensors. So here we can see the different long gauge deformation sensor topologies. So here on the left, we see a simple topology which consists of one single sensor installed in the direction of the expected strain. So it is mainly used for monitor linear structure elements like beams, which are subject to axial compression or traction, like, for example, piles and columns. And here in the center, we can see a parallel topology, which consists of two parallel sensors with equal gauge length, which are installed at different levels of the structural element cross-section. So the parallel topology is used for monitoring portions of the structure which are subject to the bending. And then here on the right, we can see the cross topology, which consists of two cross sensors installed with a predefined angle with respect to the direction of the strain line. So the aim of this topology is to detect and quantify shear strain. So the main advantage of using long gauge deformation sensors is given by the averaging of the strain over a long measurement basis. So long gauge sensors are not influenced by the local material discontinuities, such as cracks, joints, hair pockets, and inclusions that are typical of the concrete. So the measurements contain information related to the global structural behavior and not to the local material behavior that is typically provided by the short gauge sensors. The information provided with long gauge sensors is therefore more representative on the global condition of the entire structure. Okay, now let me give you a few bridge monitoring examples by bridge topology, and we can start with a cable stayed bridge. So the monitoring purpose of the cable stayed bridges is a long-term structural monitoring with a particular attention on detecting the relaxation of stress in the cables and their malfunction. So the entire bridge is to be monitored, including all the members such as the girders, the pylons, cables, and columns. So here, what we see is a typical instrumentation of a cable stay bridge. So for the deck, we recommend a parallel topology in both horizontal and vertical plane in order to determine the form shape of the girders by the double integration of the curvature function of each cell. While for the cables, a simple topology of one sensor is recommended in order to determine the strain change in the cables. In the deck cable anchoring zone that you can see here, only one cell of parallel sensors in each span is installed, while the other two cells here and here are installed close to the cable anchoring zone in order to detect relaxation or pre-stress losses in the cables. And then the first and the last cell are installed close to the battlements of the bridge in order to precisely capture the border conditions. For the cables, only a single sensor per cable is installed, since the force in cables is expected to be constant over its length. So these sensor can be installed either close to the girder or close to the pylon, depending on the accessibility during the installation. In the pylons, 3 cells are installed in the elevation above the deck, and 1 below the deck. So the first and the last cell are used to again to capture the border conditions of the pylon. And then finally, here we also have biaxial tilt meters or a GPS station, which are also proposed in order to measure rotations and the absolute displacement, in particular, of the pylons. Okay, here we have an example of a cable stayed bridge. This is the Marghera cable stayed bridge, which is located in the industrial area of Venice in Italy. So the structure consists of 7 spans of a total length of 424 meters, and this bridge has the particularity of being a curved cable stayed bridge, which has resulted in a complex design, and the monitoring system was actually very important to verify the design assumptions and also to monitor during the entire service life. So the sensors were installed during the construction in order to have a control over the most significant construction phases of the bridge, and totally 48 long gauge sensors, together with 4 inclinometers and 24 temperature sensors, were mounted on the 2 spans of the bridge, and each of the 18 cables was instrumented with a sensor, and the 12 sensors of 7-meter gauge length were embedded in the pylon. So here we can see parallel sensors were affixed onto the girder web, and the inclinometers were installed at the ends of the spans to measure rotations and the longitudinal in the longitudinal plane of the bridge. So here the deformation sensor of base length of 25 centimeters was installed on the strand of each stay cable to monitor strain variation of each cable and to detect anomalies that may indicate malfunction. The sensors were easily affixed directly on the strand using steel clamps, and the protecting coating was actually restored after the sensors installation. Here we can see the form shape of the pylon during the first tensioning phase. So we can see the pylon height, as a function of the form shape that is given in millimeter. So we can see a nice deform shape that was measured again during the first tensioning phase of the pylon. So let me say that for information, that the total cost of the monitoring system of this bridge, including the installation, was of the order of 1.75% of the total construction cost of the bridge. Okay, let's see now another bridge, the suspended bridge. So the monitoring aim of suspended bridges are still long-term structural monitoring, but with a particular attention on the detection of stress relaxation in cables and their malfunction. So the whole bridge is to be monitored, including all members like the deck, the pylons, and the cables. Right here we see the typical instrumentation. So in the deck, the sensors are surface mounted on both walls of the deck, and a parallel sensor topologies in both horizontal and vertical plane are recommended in order to determine the deform shapes, while it is sufficient a simple topology in the vertical cable to monitor strain changes in the cables themselves. So the sensor in the deck allowed to monitor not only the deck behavior, but also the vertical cables behavior. So since the horizontal component of the force in the suspension cable is typically constant, it is then possible to the installation of two sensors on both sides of the node of the cable that you can see here. And this configuration allows the determination of the horizontal force in the suspending cable by knowing the force in the vertical cables. So in the pylons, the most loaded cross section is typically the lowest one. Therefore, one cell with parallel topology is installed at the base of the pylon. And also here, tilt meters are used on the top of the pylon to measure the rotations in both vertical planes, and also at the base of the pylon to provide redundancy. Right, this is an example of a suspension bridge. This is the Manhattan Bridge in New York, and this monitoring project came up in the framework of a research program on the corrosion monitoring of the suspension bridges in New York City. So it was necessary to acquire continuous data on the strain and temperatures of the main cable and provide a baseline to evaluate the possibility of wires breakage. So 6 long gauge deformation sensors of 6 meters were installed on the main cable, and 2 Bragg rating strain sensors were installed on the anchors on individual strands. So here we can see, so here on the left, we can see the deformation sensor that were mounted on the steel conduits of the cable at about 120 degrees. And here in the center, the sensors were mounted on the 2 separate strands in the anchorage. And on the right, we can see the strain sensors that they were mounted on the anchorage I bar. So the purpose of these sensors is to measure strain on the main cable, and on one hanger as a function of the temperature variations, daily and seasonal variations, and the traffic condition. Right here we can see the strain evolution versus the time of the 3 sensors which are mounted on the suspended cable, as you can see here. And here what you can notice is that the stress that is generated on the cable is less during the night and increases during the day. And the peaks that we can see here are most likely heavy trucks that were detected when passing over the bridge. Right, now we can see another type of bridge, the arch bridge. And so the monitoring purpose is again the whole lifespan monitoring, including the concrete early age and all the critical phases of the construction of the bridge. So the load test of the bridge, it has also to be monitored, and during the service, any change in the form shape of the arch due to the load or due to the rheologic phenomena like creep and concrete shrinkage and cracking, well, they have also to be controlled and monitored. Right, here we can see again a parallel topology that it is used in the vertical plane only. So since the forces are typically transferred from the superstructure to the arch via the columns, so each segment, between the columns is instrumented with 3 cells of parallel sensors. So this configuration enables a very good interpolation of the strain and the curvatures in each segment, and also an accurate calculation of the deformed shapes of the arch and the localization of potential issues. So here we can see the same instrumentation on the other part of the bridge. Right, here this is an example, of an arch bridge. This is the Siggenthal bridge, which is a concrete arch bridge, which was built over the Limmat River close to Zurich in Switzerland. So the structural monitoring has been carried out since the completion of the construction of the bridge, but in particular during the different construction phases. So the monitoring aim at the time of the construction was to monitor the local concrete deformations, to measure the local curvatures in the vertical plane, and to calculate the perpendicular displacement of the arch by the double integration of the given curvature in each cell of parallel sensor that you can see here. The method how to calculate the deform shape of a beam. So the bridge is now instrumented with 58 long gauge deformation sensors, 2 inclinometers, and 8 temperature sensors. So pairs of parallel sensors were embedded in concrete parallel to the arch axis, which is a usual methodology. Right. So this is the construction of the vertical columns first, and then the deck over the arch. And here we can see also the towers, the 2 towers that they were used to stabilize, temporarily the bridge in order to allow the construction of the columns and of the deck. Okay, so let's see a few analysis, few results. So this is this graph shows the vertical displacement at the midspan of the arch during the scaffolding removal and the freestanding of the arch. So here it is also possible to see the different lowering phases and the periodic movement due to the daily temperature variations. And it's also interesting to notice that the vertical displacement that are due to the dead load of the arch are of the same order of magnitude as the daily movements that are due to the daily temperature variations. So this is another result. So here it is shown that the calculated radial displacement as a function of the curvature along the arch. So each curve was taken every 30 minutes during the removal of the scaffolding. And here, as expected, the arch moves inwards when the scaffolding is removed. Okay. Right. Now, finally, this is the last example, the beam bridge, which is a more simple bridge. So the monitoring aim is again long-term structural monitoring. So I always stress on this because it's very important, you know, for the integrity of the structure, and with a particular attention on the detection of unequal column settlements, rotations, and excessive vertical displacements due to creep and shrinkage in concrete, cracking, and pre-stress losses in the concrete. So also here, a parallel sensor topology is recommended, which allows the calculation of the deform shape using the double integration of the curvature function in each cell. So possible unequal settlements of the columns, cracking, or the rheologic phenomena will change the deform shapes of the beam and the vertical displacement distribution. And also the redistribution of the load will generate a change in the strain in the columns. So since the deform shape of the bridge and its vertical displacement distribution are known, so it will be easy to identify the sources of the structure malfunction. Okay, here we have an example of a beam bridge. So this is the south perimeter bridge in Winnipeg, in Canada. So it's a steel girder bridge that has recently been instrumented to continuously monitor for overloading, fatigue, and cracking due to increasing traffic and corrosion in the steel girder. So the client selected a distributed fiber optic system in order to localize and quantify abnormal strain and cracks every meter along an optical sensing cable. This is the selected SMARTape strain sensor. So in which two fibers are embedded in a composite thermoplastic tape with fiberglass reinforcement. So the sensor is very thin and very suitable to be glued on flat surface of metal. So what you can see here is the lateral view of the strain sensor installation. So the sensor was installed on the lower and upper part of the girder. The junction boxes that you see here were requested by the client in order to keep sufficient cable over length to be used for immediate cable reparation on the bridge. And the blue cable is a temperature and transmission cable to compensate the temperature on the strain cable. Okay, here we can see the strain sensor installation. So the surface needed to be clean, and the sensor was glued directly on the paint. So after bonding the sensor on the paint, the sensor was protected using a special tape for humidity and impact protection. Okay, and then finally, we also have an example on channel. So this is the Canarsie tunnel along the L line of the New York subway, which links Manhattan with Brooklyn. So in 2012, this tunnel was flooded, during the Hurricane Sandy, resulting in damage of the concrete banks that you can see here on the two sides. So here more than 4 kilometers of strain sensing cable were affixed onto the banks, covering both banks in the two parallel tunnels. So early abnormal strains to induce a collapse of the banks on the train bank are now detected by this monitoring system, which automatically triggers alarm to stop the train traffic and allows visual inspection inside the tunnel. Okay, well, thank you very much for your attention.
Thank you. Thank you, excellent, Roberto. Thank you for the presentation. We will now move on to some questions that some participants have asked. Joining the question session are Sébastien Lavoie, Project Manager at Rocktest, and René Deblois, Marketing and Sales Director. Sébastien?
Hello, everyone. Yes, thank you, Olivier. Let's start with the question. So first question here. What is the maximum length of long gauge sensors?
Yes, the maximum length is 10 meters.
Okay, and that's for all different technologies, or you have different length for various technologies?
No, not really. Well, 10 meters is for the interferometric system. While for the Bragg rating is the maximum is 2 meters.
Okay, thank you. Second question here. What kind of maintenance is required for the sensors and the data acquisition system?
Well, not really very much. It would be sufficient to clean the optical connectors, once a year. Otherwise, okay, Rocktest can provide also a maintenance and service contract where we we can do, you know, a regular maintenance on the system.
Okay. I have two more questions here. Do the presented monitoring solutions allow dynamic monitoring?
Yes. Well, basically, the examples that we saw in this presentation are for static monitoring, but we can switch from static to dynamic using the same equipment if actually it is requested, you know, by the client.
Okay. And one last question. Can the rock test monitoring system be retrofitted also to on an existing structure?
Yes, sure. Well, maybe you saw some examples when the instrumentation was already installed during the construction of the bridge, but of course the same instrumentation can be retrofitted, you know, also on existing structure, as you can see, you know, the last example, you know, the South Perimeter Bridge in Winnipeg. This is an existing structure, and the instrumentation was actually retrofitted, you know, to the bridge in order to provide, you know, a monitoring system on that existing structure. But of course, this is possible. We have to maybe to change a little bit the method, you know, to install the sensors. For example, using, you know, brackets that they will be used to install on the existing surface. But this is definitely possible. Okay, so that's all the time we have for questions. So the other questions that we have in the list, we'll answer those directly by emails to the people who've asked some questions. I'll give back the mic to Olivier for the closing remarks.
Yes, thank you, Sebastian, and thank you, Roberto. So again, if you have additional questions or any requests, you can send them directly by email to info@rocktest.com. So you can see below here on the presentation, info@rocktest.com. Hoping we can collaborate in future projects together. So thank you very much for your time today, and have a good day. Thank you, everyone. Goodbye.
Goodbye.